Thank you for the invitation, and I'm happy to be here. So my talk will be a little different because I'm not looking at stellar objects, but at extragalactic objects, but I hope I can motivate you a little bit. There can be a lot of interesting things done, and there is a lot what one can learn, and emission line objects, especially extreme emission line objects, are very different also from the observational side compared to that what a stellar continuum gives you. Which also means that there are maybe observational possibilities. Okay, before I start with that, the thank you page with the number of students who contributed over the last couple of years, the institutes, the funding agency, and thanks to Kerstin for a lot of discussion to many of the topics. Okay, so I thought, what can I do? How do I structure the talk? And so maybe I took a different approach there. I said, okay, maybe do it a little bit from the technical side. So what kind of spectrographs do we have, and what can we do with different setups? What are things which need some very special instrumentation, which can be done easily with the standard spectrograph? And I start with low spectral resolution, and I define that as R smaller than 1000. So R, lambda to delta lambda. So there are different definitions, so don't take that as the definition, but just for the sorting of the talk, I say this is low spectral resolution. So what you see there is obviously the shape of the spectrum, the spectral energy distribution. You see strong emission lines, you see strong breaks in the stellar continuum, but you don't see easily a lot of absorption lines. So what is the typical use for that? Well, obviously, for example, this was an important source for rough spectral classification, finding emission line objects, and getting redshifts. So what we do? Well, objective prisms, low resolution slit spectrographs, and okay, this is the recurrent wave, multi-object spectrograph with fibers or slitlets. I will come to the different types. Okay, just a short reminder, and I think we all know that important is, and it's the classical way to do that, we use a prism, and we put this prism at the front of our telescope. So just keep in mind, okay, we have refraction, and the refractive index is a function of lambda, and depending on what material you have, you get different reflections, so you get your spectrum. And how does it look like? This is the objective prism for the 50, 60, 70 centimeter Schmidt telescope at the Bulgarian Russian Observatory. So you have a large glass wedge with a diameter of 50 centimeters, which you put in front of the telescope, and that is what you get. This is an image which you take, wide field Schmidt telescope, and then you disperse all the objects. So you get spectrum at individual positions, a spectrum of some length, and some of these spectra have interesting substructures like this one, which has a pretty strong emission line sitting here. Some are just stellar continuum when you see the sensitivity function of your spectrum. So typical implementations that was, for example, the Macarian survey, the Hadron Quasar survey, the UCM emission line surveys. This is good for emission line objects, UV bright objects, very cool objects, so everything where you have a strong structure in your spectrum. And the big advantage is you get a lot of objects at one shot. So this is nice. But there is obviously a big problem. Since you disperse every spatial pixel, and every spatial pixel gives you a spectrum, the night sky is also dispersed and gives you a background. So the problem is you have a very much enhanced background, so you only see the brightest objects. The brightest object gives you the spectrum, and depending on how the objects are located, you get overlapping spectrum. Okay, you can take them, turn the prism, do it again. Okay. But the big step in this direction. And why this object is, this method is still relevant is if you want to do the same thing from space. So that is something why this method is still in use and is heavily used. This is an example. This is a UV image and a UV spectrum of the star-forming region NGC 604 in the galaxy M33. So you see a lot of hot stars here, and you see here the little slit dispersion. This is obviously not a prism, so this is sitting in HST. So this is a grating prism. I'll come back to that in a little minute. And it's not put on top of the mirror, but in the spectral range. So that has practical disadvantages, but still working. So this is one of the big projects which was very successful, and similar projects will also be done with the James Webb Space Telescope. So we have here a direct image. This is UV, very broad filter, HST. So you see a lot of galaxies and the star here. And then you have this prism put in, not in front of the telescope, but in below the mirror. So you get the same effect with some disadvantage because you are not in a parallel beam. And you get it dispersed and you see interesting objects. You see something here, you see something here, you see something here. So these objects are emission line objects. So an example here, that would be the image. That is the dispersed spectrum. This is the trace. And what we see here at very low spectral resolution, we see the two oxygen lines, the forbidden oxygen lines, H beta, H gamma, H delta. The two oxygen lines are more or less blended into one emission P. But for that one, we get at objects at this magnitude a very good redshift. So this is a very effective way to find emission line objects and get redshifts for even very, very highly redshifted objects. So it will be done in the future. But still, for demonstration and teaching purposes, it's still an interesting thing to have a low dispersion element in your spectral, in your telescope, because you get a lot of spectra in one shot. Okay, obviously you want to do that with a grating. The problem is if you do a standard grating spectrograph as like that, well, you're not on the optical axis. So there's something which you have to keep in mind. You find the different way. And this is normally not only applied to the low resolution spectrographs, but also the intermediate resolution. I would define that as R between 1,000 and 10,000. And there you have a lot more which you can do. Of course, you can measure individual emission lines, use that for diagnostics. You have the stellar continuum. You have easily stellar wind lines. You have, at the higher end there, also photospheric lines. You get also limited kinematics. So what you have is a long list of, that is the workhorse spectrographs which we currently have at probably any size of telescopes, up to the 8-10 meter class telescopes. What do we gain if we have now more spectral resolution? Well, spectral resolution, as this long old diagram shows, spectral resolution is when we have two lines, or line components, which we distinguish, and because each of these lines has vary functions, so we have a local minimum, we have the second maximum, so we have resolved the two lines, the two emission lines, if the distance of the maxima is larger than the full width at half maximum of the lines. So that's the point. This one, there are still two components inside, but this will be unresolved. Okay, now we have to also keep in mind, we have the pixelation of the CCD or the CMOS detector. So if you have huge pixels here, then this dominates your resolution. So you have to be a little careful to match spectrograph and detector. I will come back to the spectrum because there's a lot of interesting science in here, but I wanted to show you there is another often forgotten effect for emission lines if you go to higher spectral resolution. If you go to higher spectral resolution, you distribute the light over more resolution elements. Okay, so that means you need longer integration times for the same spectral noise. But if you have very faint lines, so something like that, nearly impossible to see here. Well, okay, here we have a couple of very strong lines in here too. But if you have small, weak lines, then spectral resolution helps. If you go to higher and higher spectral resolution, you have no continuum which you're folding into your line. So that means up to the spectral resolution of the intrinsic width of the line, you get. So there is something like a sweet spot in resolution. If you resolve much stronger, then okay, then you distribute again over many pixels. But if you are in the resolution which samples the intrinsic line width correctly, then you get it. So if you want to have very faint lines, emission lines, then it can be helpful to go to higher spectral resolution. Okay, so what we do, because we want to have relatively high spectral resolution, but also a high a large free spectral range. So one good trick is to build something like a twin spectrograph. So you use the spectrograph and you use a beam splitter. You come here from the telescope down and you split the blue and the red light with a dichroic mirror. So one of that goes in the blue optimized spectrograph and the other part of the light goes to the red optimized spectrograph. So that would be some kind of dichroic beam splitter, and you split the line and then you have a small area where you lose, because at that point you will have decreased sensitivity. But you double your spectral range, and you can optimize your spectrograph either for the blue or for the red, which is good for coatings, for choosing the right glass, choosing the right gradients. So that's a classical thing to do. Another thing, and there we come back to the idea of putting a disperser into your spectral path. If you have convergent beam, then you have a lot of problems. Optimally would be use parallel beam, as you have when you put the prism or the grating at the top of your telescope, then you have a parallel beam. So how do you do a parallel beam? The trick is easy. You build a focal reducer. So you come from the telescope, you have the telescope, you come to the focal plane, and then you put a field lens, and then you have a collimator lens, and then you have here the camera lens, and between the collimator and the camera lens, you have an area where you have again parallel beam. And that is a very interesting design, which is a little tricky because you have to take care of the optical aberrations of your system, but you can do a lot of these things. You can use the same instrument as an imager. Well, you just put a filter in here. It's also nice to have the filter in a parallel beam. But you can also put a dispersing element here. And then you put here a slit mask, either a slit or many slits. So you have a multi-object spectrum. So put here a dispersing element, but okay, if you have a dispersing element, then obviously you move out of the axis of the spectrograph. That can be avoided if you use prisms. So just as an example, this is probably the most famous and also most successful of this kind of spectrographs. This is FORCE at the VLT 8.2 meter telescope. So you have here the flange, and you come here in the collimator section, and you have here a filter wheel, and then you have a wheel for different filters, but also for dispersing elements. Okay. The trick to make this all work is a grism. What is a grism? The grism is a grating plus a prism. So what you do is you make a sandwich between a grating, a transmission grating, and a prism. The prism pre-selects you the spectral range, and it moves your light back, or the spectrum back into the optical axis of your spectrograph. So put that in. That is an actual prism, how it looks like. That is the schematic. So you have the prism effect, and then you have the grating put on top of it. And with that, you can do either low or high spectral resolution. You can exchange them easily, and you have a straight line path, so you have a very stable instrument. Okay, so this is just another example for different prisms with different grooves per millimeter, spectral blaze, effective sensitivity, and you see here the effectivity of this setup is really high. Then you can define low and intermediate spectral resolution. You can even go beyond that, and that is a development during the last couple of years. You also have heard of that. Volume phase holographic gratings, these are the big rage now in astronomy, because you have a way to produce grating rules, or the ruling of the grating, much, much closer. And that means you can get a first high sensitivity, but also high spectral resolution. So it's similar. The idea is you create a hologram in a gelatin layer between two glass plates, or one glass plate or one glass prism. And that is similar to a Bragg reflection in a crystal. And that is how they look like. This would be a VPH grating for the ESO-VIMOS spectrograph. You see, this is a prism. So you have the prism here and here. You have here the layer, is this or this two glass plates with the gelatin layer in between. This is the dispersing element. And then you get, again, very high efficiency at moderate or higher spectral resolution. Okay. And the good thing is, since you have now a spectrograph where you can put whatever in your focal plane, it has not to be a slit, it could be a curved slit, but it could be also a lot of slitlets. This is an example what Kerstin did on 30 Doradus. We have here 30 Doradus. We have here a lot of slitlets on massive stars in the core of 30 Doradus. And we have here a set of spectra. On contrary to the objective prism, or the prism just put in without the slit mask, you suppress the background. And you have all this spectra, but the spectra are always moved. You see here the skylines are always at different positions because, well, the spectrum would be dispersed here or would be dispersed there. Okay, so then you need obviously a little bit of planning software and some way to do that in an efficient way. For example, with a milling machine, or do it in a different way. Okay, so at that point, that's great, but still, we have only slits. The next step, which we can do, is say, what I'm really interested, and there we are away from the stars, somewhat, to extended objects, galaxies, emission line galaxies. What we want to have is a 2D image in many, many individual frames or slices of spectral resolution. And that we call an integral field spectrograph. And there are different types of them, how to realize that, so we can discuss on that in a later way. All of them have about this, all of them work, they have all advantages and disadvantages. But the idea is really we have a focal plane, we have an image, and we cut that into little areas, and then these areas we rearrange into a slit, and then the spectrograph gives us for every of these spaxels a spectrum. And then we have a data cube, then we can invert that to having images or every element of spectral resolution. So there was several surveys. This was one very big one where I was involved, where we observed 700 galaxies with the specific IFU, at that time the largest IFU built. So that would be the SDSS image, that would be our IFU, and then we had a low resolution spectrum and a higher resolution spectrum in the blue, which we then use to derive a lot of parameters like star formation, spatial resolve, age, spatial resolve, dust content, spatial resolve, star formation rate, emission line strength, metallicity. Okay. Now I talked a lot about techniques. Hopefully you get some a little more interesting then, what can we then learn from intermediate dispersion spectra? And there's a lot. If we, again, I'm staying away from stars, mostly. If you look at the emission line spectra, you can derive the electron temperature, you can derive the electron density, you can derive the hardness of the radiation field, elemental abundances, well, at least for the elements where we have emission lines from. We can also look for hints where Lyman continuum photons are leaking out of the galaxy, which is a very important process when we want to understand the surroundings of galaxies, and at very high redshift, how the universe made this phase transition from a neutral intergalactic medium to the ionized intergalactic medium which we observe now. In some way, the intergalactic medium had to be ionized, and that can be stars, that can be quasars, but we have to find out. So that would be very important. And the trick here is, well, at very high redshift, we see point sources and we learn only limited, but if we find the right objects in the local universe, we can learn a lot. And we can do some kinematics, and we can derive star formation histories. Let's go through a couple of them. So that was a nice analysis. Nichols and Mike Dopita did on a number of small, compact, relatively compact dwarf galaxies. And these are the spectra which they are obtained. Well, they are dominated by a number of lines, and they are typically groups which you immediately can recognize. So this is O3, O3, the two forbidden oxygen-3 lines. Here is H beta. So this is a clear sign. This is an ionized region. And we have here H alpha and sulfur 2, and then very tiny here nitrogen 2. Because these are dwarf galaxies, they are low metallicity, so nitrogen is done. You can immediately see from that all of them are really metal objects. And then you have the oxygen 2 line, the Balmer series, you see here the Balmer lines, and this is, well, a limited spectral range. It's not the full optical range, but you see that. And most of the information which we get here is from the emission lines. So the signal to noise in the continuum is great, but I think you don't need a lot of this signal to noise in the continuum. If you just look at these 5 lines and you can work with them, the signal to noise which you need is determined by the signal to noise of these lines, not the continuum. And then you can do theory and say, okay, these lines have different ionization potentials, they come from different levels in their atomic structure. So you have lines which are sensitive to the ionization degree, to density, to temperature, which is again the ionization. And then you can calculate, or let the software calculate, model grids, and you put in your measurements. And you see here, this is oxygen 3 to sulfur 2, nitrogen 2 to oxygen 2. These are all bright lines, and all these are bright line ratios. And you can now see where these galaxies fall in theoretical predictions for metallicity. This is, what is it, 30s of solar, and that would be half solar. And that direction here would be the ionization parameter. So you have relatively soft, and here we have harder and harder ionization fields. So with very or relatively low low signal to noise, relatively low signal to noise, you can get parameters of this H2 regions, of these starburst regions. Well, obviously, the better the signal to noise, the better it is, the more lines you can see, and we'll come back to them. But you can play interesting games already. You can, for example, look at the ratio, the abundances. You can derive the abundances too. And then you can look how oxygen and the ratio between nitrogen and oxygen play a role. And the interesting thing is, this is not a one-to-one correlation, because oxygen and nitrogen are formed differently. Oxygen is produced in massive stars only, and in supernova explosions. type 2, type 1b, 1c, so massive stars, core column supernova. Nitrogen can be produced on two ways, either in Wolf-Rayet stars, that would be that which is correlated with the oxygen abundance, and in the second way, in intermediate mass stars. What that means, if you have a burst in star formation, the nitrogen ratio would give you, well, the time since the burst, because in that time no oxygen is produced, but gradually the nitrogen builds up. So if you move upward in that direction. So that is a potential clock, but this is a little more complicated than I described it here. But we are really deep in galaxy evolution here. And we can look for this Lyman continuum leaker. Well, Lyman continuum leaker would be, we look at Lyman continuum below 912 angstroms. So this is way in the UV. So we don't have a space telescope to do that. Well, if you have not time at the HST, as long as we're still working. But they are indirect tracer. When would an H2 region lose Lyman continuum photons? If the stars produce more than the H2 region absorbs. So if you have not enough material there are leftover Lyman continuum photons which can escape. We call that a density-bound H2 region. And this would show up in a diagram, a delta S2, delta oxygen 2.3. So these are parameters built from these lines in this area. And well, this was work which we are hopefully submitting next week for a number of dwarf galaxies which are populating the area here. And these green ones are proven Lyman continuum emitters. So our colleague Yuri Isotov had HST spectra, and he could show these are leakers, and the blues are the ones where we predict that they are leaker. And you see, it seems to work very nice. If you have not a single spectrum, not a point or a slit, but you have the 2D spectroscopy. So you can add the information where are these individual lines. Then you can look at maps of lines. So this is the pure H-alpha image of a galaxy. And this is a deviation image for where we would expect, well, which we could prove, which is leaking. So we would see this, and these are the positions of two very young star clusters, and this blue area here would be density bound, contrary to the red areas which would be ionization bound. So this galaxy is a leaker, and we see where it is leaking out, perpendicular to the disk of the galaxy. Okay, so this is another of these galaxies. So we have here an HST image, I made the overlay. This is very high contrast. You see some filaments out here, and you see the inner part, there is a bubble about half kiloparsec in diameter. And when I took a spectrum, a slit over here, you see here now the lines. This is H-alpha, this is nitrogen 2. Here is the helium line, and here are the two sulfur lines. And if I take H-beta, H-alpha, sulfur 2, then we see this spectrum, well, it's not fully resolved. Well, the resolution was below 2000. But still, this cannot be fitted with a single Gaussian. You need two Gaussians split by 300 kilometers per second. So whatever is here is moving away in both directions with 300 kilometers per second. For such a low mass galaxy, this material will be gone. So this is a little bit of kinematic even at low spectral resolution, well, intermediate spectral resolution. And then a number of other interesting things which you can do around 8,000, 10,000 for the kinematics of very, very bright H2 regions in these galaxies. Okay, and it makes sense, these 300 kilometers, because here we have also a slightly diffuse X-ray source which also would fit. Okay. I commented, you can also do something on star formation history, and then you have to believe models. But this is our spectrum, the orange one. You see all the emission lines, but you see also there is rise of the continuum. So there is a blue star population, and if you look a little careful, there are some hints for lines. There are some breaks here. There's another break here. So this is the Balmer break, this is the Paschen break, and that we can model. Model single stellar populations that the code run and run and run, and then we see how much stars are formed as a function of time. This is something which is surely tricky. You need good signal to noise, and you have to believe your models, but there are a couple of them out there which can be also compared. So our claim here is a single burst does not the job. You need some historic, well, not only 10 to the 6, but also 10 to the 7 year clues in strength. Another burst which pre-structures the medium in galaxies like that. Okay, and now high resolution. High resolution are beyond, say, 10,000. So what we can do, but real kinematics, because we see multiple lines components. We can see interstellar absorption lines. We can detect faint lines where you have improvement for the faint light detection. And we can do a lot of photospheric lines with stellar spectroscopy, obviously. So what we can do? Well, we can build high-resolution slit spectrographs with VPHs, so that is probably an interesting way of the future. We use echelle spectrographs with fibers or slits. Long slit echelle spectrographs, unfortunately, where we have a long slit and just one order, they become rare, unfortunately, at big telescopes. Which Kerstin and I don't like a lot, but okay, that's the way, because these fiber-fed echelle spectrographs are great for planet search, for example. So this is in book. We can do multi-object spectrographs, because we just have the fibers. When we have many fibers, we feed them in the spectrograph, no problem. Integral field spectrograph, then Fabry-Perot interferometers and Fourier transform spectrographs. These are two interesting things which I thought may interest you to have a look at. Okay, example of that, what we can do for kinematic analysis. This is an echellogram or the output of an echelle spectrograph. So you have a lot of orders. We have two CCDs, a descending mosaic, and you have a lot of these orders. And then we cut out what we really want to have is H alpha, probably with a few other lines. So how do we cut out that? Because the slit length here can only be a couple of arc seconds. Because if the slit is too large, then we overlap with the next order. So what we do is we cut that out, not putting this order selecting grating, and replace it with a filter, with a narrowband filter. Then we have only this order or a part of this order. And then we get that, what Kerstin already showed. This time, this is Eta Carina. We have the interstellar, or the lines of the H2 region, H alpha, nitrogen 2, nitrogen 2, and a lot of blobs with different velocities. So that must be H alpha, that must be nitrogen 2, and that must be this nitrogen 2. These blobs here have a different velocity. And maybe that is nitrogen 2 direction. You see also that nitrogen 2 is very strong here. And you see that the split is clearer in the nitrogen 2 lines than in H alpha. Well, obviously, if you have 10,000 degrees, a heavier element gives you a better spectral resolution. Because this is a heavier element, you will have smaller motions. Okay, so how do you interpret that? Kerstin showed that already, just as a simplified, right? This is S61, was shown before. We put a spectrum, a slit over it. This is the slit here. What do we expect? We expect, if you have this is our dispersion direction, so that would be the spectrum, that would be the slit direction. So here we get continuum, that's the star. And we have then the H alpha line, which would be here and here small, and the split gets larger. If you have a round bubble, if it runs here, you have the maximum radial velocity towards you and from away from you. And at the rim, you have no split anymore, because the radial velocity will be 0, or the difference in the radial velocity. So that's a very simplified case. Then you fit that, and you probably can do that. This is the original spectrum in the slit center, and you see nice Doppler ellipses here, and you can fit them and get kinematics. So where are the limits for that? Well, this is a relatively simplified case, but what about a galaxy? If you have something where you don't resolve the object perfectly. And these are the same kind of spectra, but taken from, this is the original spectrum, from a galaxy, this galaxy. So this is a slit which runs across this galaxy. This is R22,500. You see individual knots of H2, some of them have some extension in velocity. So in that case, so we have here the slit, and here the velocity or the dispersion axis. This now is the same spectrum smoothed to R7000. And this is the same spectrum smoothed to R4200. And the noise adapted, that we have roughly the same noise in the background for all the images. And you see all these faint features here, they go away. Because the central line dominates everything. You don't have the signal to noise anymore, and you have not the split, enough split to see the faint high velocity features. So my claim is, or Kerstin and my claim in this paper was, well, you need that resolution. If you go with this resolution, you will lose a lot of these important high velocity features, which dominate all the interpretation for example, gas flowing out of a galaxy. Okay, that I showed you already. This was our slit map. So we put individual slit here. Unfortunately, this is not a fully sampled map, but okay, at least kind of a mapping. These are the echellograms, and I've just marked here a number of these regions where we have velocity offsets of more than 100. And since this is 10,000 degree, roughly 10,000 degree gas, so this is Mach 10. So these are the regions where you have significant velocities beyond the sound speed. And that correlates very well the regions where we have these structures with the X-ray emission, which we also observe in this galaxy. So this red is H alpha, blue is the X-ray emission. So you learn immediately something if you look at the kinematics and compare it with a different wavelength range. So a lot of this work is really multi-wavelengths, and contributions to the one or the other is always helpful and it's always needed. Okay, so do we have another way to get high resolution spectra? Because low slit shells are rare, long slit IFU fed objects, there are also one or two places only currently in the world who have something like that, and there the sensitivity is not very good. One way is a Fabry-Perot Interferometer. So what is this? You have two plates, there's an interference gap, and you get interference if you have light infall by reflecting on transmission of the structures. What you get is then a very typical pattern where the width of this line is depending on d and lambda. And this is a repeating pattern, so you get these rings again and again and again. So transmission goes up, transmission goes down in this typical pattern with wavelengths. So you select one of these orders, and then this order or this line will move along in the spectral range, in a free spectral range. So the unfortunate thing is, the narrower the line, the higher your spectral resolution, but the smaller is the free spectral range. So you change now the gap between the lines, and you see how this ring moves out. So you trace along the line. So what you can do is say, okay, I have only that field, I integrate everything up. I have a very deep spectrum with, say, 5 minutes resolution at the sky, which is good, and you can play interesting things with it. But I want to have a 3D cube. So how to do that? Well, I have to flat field it, and I have to do a wavelength calibration. So I measure the neon line, or the comparison line, and also scan that with the changing the width of between the two planes. And then we can calculate the phase for the motion of the lines, because we see that in our spectrum, we see that the neon line, we know what the position of the neon line is, and we can calculate. So here the raw data, the flat fielding for each of the steps. And here we have the neon map, and now we compare as we do for every dot on these 2D slices, or that finally the whole cube. We know what the wavelength is. That means we get a phase calibrated cube. And that would be a phase calibrated cube in the sky. We would have the channel 1, and we run now through these individual channels. Each would be the resolution, half of the resolution element. And you see, this is continuum. And then suddenly, H2 regions pop up, so this is H alpha, and then move over the galaxy. So what we have here is the rotation curve of this galaxy in 2D. Or here, for a dwarf galaxy, so we have in the background the HST image, and this is a Fabry-Perot data cube which we analyzed together, or with Michel Marcelin, and we see the velocity field. We clearly see, first it is more extended than the HST, but the important thing is the velocity is not a simple velocity field, but we have deviations here and here. One here, here. Rotation runs in that direction, and we have also some deviations here. So what we get is R40,000, spatial resolution 2 arc seconds, which is given through the scene, and we get the velocity field, and this implies here a galactic outflow or wind for this very low mass galaxy with about 100 kilometers per second. Model the rotation curve, subtract that, and then look for the residuals. We can do that also with other objects. This is another H alpha image. This time it's a classical H alpha image for NGC 1569, which is really bright at the sky, easy to get the spectrum. And then we can use pixel for pixel the way to look for turbulence. And depending on where in this diagram this intensity and velocity or sigma of the line width, it is we have different kind of objects. So we have the normal turbulent ISM, we have H2 regions, shells, and probably compact envelopes like supernova remnants or LBVs of overheat. And we can do that also with integral field spectrographs. If we have it, fortunately, there will be an ELT spectrograph with enough spectral resolution. But there is no reason we could also do that for smaller telescopes. And that is exactly what the Sloan collaboration is now doing. They're building a number of these spectrographs for 40-centimeter telescopes to look at galactic emission and do galactic ISM physics with them. The final thing which I wanted to show is the Fourier transform spectrum. This is another of these tricky things. So we have here, the idea is you have a fixed mirror, you have the detector, you have a beam splitter here, you have a mirror too. And now if you move the optical path between these two mirrors, you get a signal, and you add these two optical paths, then you get a signal in the detector. And the interesting thing is that depending on how you do that, you get a lower and higher resolution spectrum. You get something like 3D spectroscopy with an adjustable spectral resolution. So if you get this interferometer and you transform it into a spectrum, and then you go to higher and higher, smaller and smaller steps, when you get a higher and higher spectral resolution. The big problem here is And this is used. There is one instrument in the Pergite at the CFHT, led by Laurent Trissin. The problem is the spectra look not very nice. So these are not Gaussian lines. So to analyze that, you have to be very careful to do it in the right way. But still, to get a 2D velocity field as shown here. But I'm not recommending to try that because it is a really tricky thing, and there are only a few of them realized, most of them in solar physics, but this one is now shown to work also for galaxies. Okay. What else could be interesting? Well, this could be edges of the spectral range. The new detector technology now allows us to extend the optical spectral range beyond 7,000 angstroms, so to a micron or so. And also going down to the UV cutoff of our atmosphere. Obviously, we lose and lose and lose more light, or we get more and more problems with the skylights, but we can go there. And the first spectrograph which really did this full spectral range was the UVIS at the VLT. This is a tricky thing, especially in the UV, because of the coatings and all that. A huge step will be CUBES, a spectrograph which will be defined for this cut-off region with R20,000, and to get high sensitivity that will be operating. Okay, so this spectrum they have shown before, though that was done by Adam Enders in his bachelor thesis. He is now a PhD student. And we see a number of these lines popping up here in the red part of the spectrum. And we have also a number of interesting lines here from very high ionization features in the blue, but we also go here more into the blue. But this is a fiber spectrum. What we really want to do is go very blue. So I will not go through this list. This is one of the few spectra which goes very blue. This is an AGN spectrum, and you see 3700, you have the oxygen 2 line, 3400, we have a huge neon 5 line, and we have funny O3 lines, we have O3 recombination line, an iron 7 line, pretty strong here, an iron 6 line, so stuff which we don't normally have, and because there are no strong transitions for these lines in the normal optical spectrum. And so I made the try, used the best UV spectrum of this ground object, so integrating of this knot. So this is a very low metallicity galaxy. And what did I find? Nitrogen 5. Very nicely, actually very broad. Well, signal to noise is not great, yes, right, but it's 3346. Here, the iron 5 line is there too. This is easy, 4227. And we have 7 weaker lines of iron 5, iron 6, iron 7. So this is really interesting if you are interested in hot gas and hard ionization fields. And it is a mostly unexplored region because of the difficulty to build instruments. And you have a lot of, and this is the same spectrum, and you see now this high spectral resolution, so the O2 doublet is split. You have here the 3 lines. These are really strong lines, so one can even do kinematics if you have something like a decent high resolution or intermediate resolution spectrum. Problem is, there are none out there, so one has to think of how to build that to go, well, as far as one can go. And for that, I stop here with a lot of ideas, a lot of possibilities, or maybe sorting out what is possible. And the important thing, I hope I convey, is these emission lines are extremely strong. So they have, if you look at the equivalent widths, they are not tens, some of them are hundreds. So that means even if you have a relatively small telescope, you have decent, the right spectral resolution, you will pick up the emission lines. One has now to explore how far one can go there. The people from Sloan are obviously convinced that we can do a lot with 40 centimeter glass telescopes if you have an instrument like that. If I can build them at a decent price level, I'm not sure yet. But I think also their input will be helpful. Thank you.
So,
yeah, please.
The Fabry-Perot,
yeah,
that is like scanning. Correct me if I'm wrong. It's scanning through a filter. So you basically can scan at a very high resolution, depending on the step size, through certain lines of interest. Right?
So the parameters which go in here is, well, the wavelengths, the order API, and the D, which is the distance between these two parallel plates. So depending on how you, the finesse, the F, is the defining parameter which gives you the spectral resolution. So the width of this repeating maxima in the Fabry-Perot intervals.
So the resolution is simply set by the step size. You move the two.
Yes, you move that. The step size should be adapted to the spectral, to the finesse which you have. So you can have 32 steps, but if you have, you're sampling only that function here, you don't gain the oversampling. So it's two things. You can run the Fabry-Perot in two ways. The one is scanning, as we discussed, and then you have to do the phase calibration, or you use it as just one shoot spectrograph. Then you have the spatial resolution is just your field of view, but the spectral resolution is the width, well, the finesse, given to the finesse. So you integrate the whole ring, so you get Jacquinot advantage, so you go very deep, but you have low spatial resolution. But the spectrum is very, very sensitive. This is what, for example, the WAM survey from the Wisconsin Interstellar Medium Group did. So if you look at WAM, WHAM, they make a map of the diffuse ionized, the diffuse H alpha of our Milky Way, and they're extremely faint. So they really show that the whole sky is full with H alpha because they have this huge sensitivity.
And are you limited by the, for a point source, by the size of the point source? So would AO bring you advantages? Or?
No. The problem here is this is good for diffuse material, but if you have a point source, then you don't gain, because then you have a continuum, and that means you have overlapping rings, and then it does not work that well. So if you want to look continuum sources, you have to do integral field spectroscopy in a classical way. That does not work with the Fabry-Perot. It was tried, but it's simply not as efficient. Okay. Yeah, please.
For non-profi astronomers, it's a problem for high-resolution spectrographs, because you need a lot of time for exposure time to get sensible spectra.
Right.
What can we do?
Well, one interesting point, as I said, if you have an extremely bright line like H alpha or oxygen 3, then a galactic H2 region, or a region which fills your slit, your position, which is near point-like or slightly extended, then you will have a very high resolution profile of the line. Okay. And if you have something like beyond, say, 10,000, then you have the width of the line. And the width of the line of such regions contain interesting information. For example, is it thermal or is it larger than that? So for 10,000 degree, you would have some 10, 15 kilometers line width. If you measure 35 kilometers line width, so there must be turbulent motions inside. So what you have is a handle on the turbulence.
Okay.
And this, interesting, is not clear if that is dominated by the energy input of the massive stars or the underlying gravitational field. So there is a claim, and it seems that that works. There is a correlation between the line width and the intensity.
Okay.
So that would be an interesting distance indicator. That is just one application which one could do. Another thing is, which unfortunately I have forgot to put in, is if you have a spectrum and suddenly the line shape changes, then one of characteristic stars would suddenly be there. Why? A supernova imposter or an LBV in eruption. If there is enough additional light from a stellar source, then the line shape will change from a symmetric to a p-Cygni profile, which really happened in the dwarf galaxy PHL 291, where about 2008 p-Cygni lines appeared, and 2018 they disappeared.
Okay.
So the interpretation is most probably some kind of. This is, if that is manageable with intermediate class size telescope, I think nobody really knows. Probably for very bright objects, could be. Yeah.
So you mentioned some new type of grading.
Yeah. The volume phase holographic gratings.
Yeah.
And yeah, this is the, well, not that new, it's the last 15 years or so, that you have glass plates and gelatin layer in between, and you use a laser to produce a regular pattern in there, which then is used to disperse light. And because you have this laser, you can do very small dots, very small point, and that means you can get a high density of the grooves or points. This is more like points, like a Bragg grating, but you get them very thin, and that means you can produce high resolution and high throughput. And combine that with a grism, then you have a very efficient way for this focal reducer spectrograph, or do it in a simple transmission grating spectrograph. You will gain in sensitivity. The limiting factor is that these gratings, compared to classical gratings, will have a smaller spectral range. Not hugely smaller, but still, it's an effect. And they are becoming more mainstream now, so it's not that they produce one by one as 10 years ago. Okay. Thank you.